This video is going to be about simple harmonic motion. Simple harmonic motion is a very special case of oscillation where three things must be true. The period and the amplitude must be constant, the period is independent of the amplitude, and the displacement, velocity, and acceleration are going to be sine or cosine functions of time. Unless all three things listed here are true, it's not simple harmonic motion. So you have to have all of these specific traits of the motion in order for your oscillation to be a simple harmonic motion. So if those are the three conditions to have simple harmonic motion, what do we need to set up simple harmonic motion? So one of the most important things you're going to need is something called a restoring force. So if I were to draw my pendulum at equilibrium, so I have my pendulum sitting here at equilibrium. If it were displaced to the right, it's going to need a force in order to pull it back toward the equilibrium position. And this force is my restoring force. The restoring force, in the case of the pendulum and all simple harmonic motion, is always going to point toward the equilibrium position. So if my pendulum right here is in my equilibrium position, when my pendulum swings to have a negative displacement, the restoring force is now going to point forward toward the equilibrium position. So the restoring force will always point back toward the equilibrium position of the system so that it restores the pendulum back to its original position. In the case of simple harmonic motion, this restoring force is very specific to what it must be doing. So in simple harmonic motion, the restoring force's magnitude is always proportional to the displacement of the body from the equilibrium position. Additionally, the direction of the restoring force is always pointed toward the equilibrium position. Because the direction of the restoring force is always pointing toward the equilibrium position, the acceleration of the pendulum will also always point toward the equilibrium position. So if the acceleration is always opposite to the displacement, we can express this mathematically as acceleration is proportional to negative displacement. If we wanted to look at this graphically, draw this on our x and y axes. So if I would put acceleration on my y-axis and displacement on my x-axis, I see that if I were to, let's draw out a pendulum here. So if I were to have my pendulum at its most displaced to the left, right, that means the force is going to be greatest toward my equilibrium position. So if that's my equilibrium position there, the force is greatest pointing toward that, pointing back toward the equilibrium position. When my displacement is at its most negative. So when my displacement is at its most negative, my acceleration and my force are also at their highest. If I were to push my pendulum the opposite direction, so my pendulum is at its greatest displacement to the right, my restoring force and therefore my acceleration would point to the left. So therefore my acceleration would also point to the left. So when my displacement is most positive, my acceleration is at its most negative. So I put a point there. If we look at our acceleration and our displacement, so when we're at our equilibrium position, right here, when we are at our equilibrium position, we have zero displacement, and therefore zero acceleration, because the two are proportional. If we connect these up with a line, draw a straight line through, I get this graph like this. So this graph is good to remember because it shows the mathematical relationship of acceleration being proportional to negative displacement for a simple harmonic oscillator.